We'll continue from this statement. We have just discussed this stratum H mu as a complex manifold of dimension 2G plus and minus 1. Nevertheless, surprisingly, this H mu can be disconnected. Okay. So maybe let me put a remark. So for special mu, I'll be more precise in a second. This space H mu can be disconnected. Okay. So it looks bad. You have a disconnected space. Nevertheless, it's not that much disconnected. It can be disconnected, but in any case, it has at most 3 disconnected components. Connected components. Yeah. In other words, I mean, even if it's disconnected, there are not too many components, up to 3. Okay, so let me put the result first and then give you some example to see the disconnectedness. Okay.
But each fiber has the same dimension.
There's no fiber. I'm saying I fix mu.
No, over mg.
It may map to a proper subset of mg. If you look at this dimension, it might be smaller than 3g minus 3. Yeah, I'm said it's only for special mu. If you take, say, the open subset of Hodge bundle, then it certainly is connected. Okay, you're right in the sense that if you take mu general, so I will be precise what I mean by special mu, but I just want to point it out. It could be disconnected. But in any case, there is a theorem due to Kontsevich and Zorich about 15 years ago. So it's basically, so I won't be precise, just say the kind of researchers, I mean they classified connected components of H mu for all mu. Okay, so based on their results, we know H mu has at most 3 connected components. And they also provide information, some geometric structure that distinguish the actual component. So it's a bit long statement depending on the signature of mu, but let me put it in this short way. So you have a complete classification. In other words, if you give me a mu according to their classification, you know immediately how many components are there. But let me give you an example to convince you at least it can be disconnected. Let's do an example. Let me take the genus to be 3. And let me consider a very special 0 type mu. So what is 2g minus 3? Sorry, 2g minus 2 in this case. 2g minus 2 is 4, right? So I need a partition of 4. I take a partition with a single entry. That means I consider a unique series of 1 order 4. So let's take mu equal to 4. So i.e., so the space H mu in this case is 4 parameterize x omega, where x is genus 3, and omega has a unique 0 of 1 order 4 times the point P. Okay, so this is my space H4. I claim in this case it's disconnected. It has 2 connected components. So indeed, so in this case H4 has 2 connected components. Let me produce them for you. Okay. So let me give you the 2 connected components. And from this example, you will see actually the underlying geometric structures that distinguish these connected components in general. So let me give them names. So H4, the first one I called hype. standing for hyperelliptic. And I will say disjoint union is another one. I call it H4 odd. I'll explain this terminology later. But let me start from this hype thing. Okay, so first it is a subspace of the total thing H4. Okay, so I claim here I still have this pair x omega is before x is in 3, omega is well, now because this hype actually require x is hyperelliptic. Okay, what is hyperelliptic? Let's define it in case you haven't seen. Hyperelliptic just means this, there exists a double cover from x to p1. Okay, this is called a hyperelliptic double cover. It's a 2-to-1 double cover. And if you have a double cover of p1 of genus G, by the Riemann-Horst formula, there will be 2G plus 2 ramification points in X, right? These are called Warshaw's points of the hyperelliptic curve X, or the just ramification points of this branch cover. In this case, I require this point P to be like one of the Warshaw's points, or like this ramification points. And this for P, where P is a Warshaw's point. That is a ramification point of this double cover. I mean, if you know a little bit about the structure of hyperelliptic curves, actually, if you take any Warshaw's point, and in general, if you have a genus G hyperelliptic curve, then 2G minus 2 times P is always a canonical divisor. So what is a canonical divisor? Just means it gives you a section of the canonical line bundle. That section provides this holomorphic one form omega. But let's count the dimension of this guy. The dimension of this, the complex dimension. When I say dimension, usually means a complex dimension. Okay. Well, look. So I only have finite many Warshaw's points, right? So this locus, whatever it is, has dimension equal to the dimension of the locus of hyperelliptic curves, right? Because when fixing a hyperelliptic curve, there are only finite many ramification points. That does not add up to the dimension. Hyperelliptic, in this case, genus 3 curves. Now this complex dimension is in general is equals 2G minus 1. In this case, genus 3 is 2 times 3 minus 1 is 5. Sorry, I have to do one more correction. This is really the tricky part. Sorry. Well, I mean, look, so I'm describing the associate 0 of omega, right? But I can consider 2 times omega, 3 times omega. They all have the same underlying 0. So my space is not only about the underlying 0, but I also rescale omega, right? That means I should say this is really is equals 1 plus this 1 comes from rescaling omega while fixing P. In other words, if you only consider the underlying divisor, you get the dimension equal to the dimension of the locus hyperelliptic curves. But even fixing P, I can rescale omega by any non-zero complex number that adds one more dimension to the space, right? Because I consider space of differentials. Differentials can rescale without changing the underlying zeros. So this is 1 plus the locus of genus G hyperelliptic curves in general has dimension 2G minus 1. In this case, 2 times 3 is 6. By the way, how do you know the locus of hyperelliptic curves of genus G is 2G minus 1? So I told you, so this branch cover if this is genus G, we'll have 2G plus 2 branch points, right? This is by Riemann-Hurwitz. I have a genus G cover, 2 is genus 0, and of degree 2 by Riemann-Hurwitz, you get 2G plus 2 simple branch points. And conversely, you can show that once I choose 2G plus 2 points to be my ramification, branch points in P1, that uniquely determines such a double cover up to isomorphism. And it looks like I can just get 2G plus 2 dimensional space, right, for hybrid curves, because I can choose 2G plus 2 points. Why this is 2G minus 1? Well, just because P1 has a 3-dimensional automorphism. So I can fix 3 points to be 0, 1, infinity. That leaves the other 2G minus 1 points vary. So that gives you the locus dimension of the space of hyperelliptic genus G curves. Again, this extra dimension comes from rescaling omega. Altogether, again, the 6-dimensional space. What is the dimension of the total space? So this guy. Let's keep in mind, by the formula, it's 2G plus the number of distinct zeros. I don't have 1 0, right? Plus 1 minus 1. In this case, genus 3 has still got 6, right? I got equal dimensional. Whatever this is, it gives me a component. And you can show that the hybrid locus in this case is connected. And it's also like a complex manifold. So this is a component. Because I also know this space is smooth. Once I get equidimensional thing smooth, that must stand connected, that must stand for at least one connected component. Okay? So I have explained this component H4 hype. So that tells us this H4 hype is a connected component. There could be more. I'm going to show you the other one. Okay. But before I do that, so let's make sure this example H4 hype is clear. Any question? I get equidimensional. And I did not explain, but you can show that the locus of hybrid curve just means you have P1 choosing 2G minus 1 points is a connected space. And also it's smooth and give you a connected component.
Well, you said this complex manifold, so it implies irreducible?
No, I'm saying so if this guy is maybe further disconnected, you might have more components.
Oh,
but I know this one is connected.
If you know the connected.
Yes, it is irreducible. Yeah. Here, connected and irreducible is the same because I have a smooth total space. So is this example okay? The other one, so let me actually provide two interpretations. The first one is more elementary, but the second one is more intrinsic for this index odd. Okay. So let me, before I introduce the other component, let me put another remark. So let's consider smooth genus 3 curve, and let's consider non-hyperelliptic ones. Let's see, X is like a genus 3, non-hyperelliptic. Then the canonical line bundle, actually the sections of canonical line bundle of X gives you an embedding of the underlying genus 3 curve into, in this case, Pg minus 1 is P2. It becomes a plane curve of degree 4. X has a canonical embedding. Into P2, complex CP2 has a degree 4 plane curve, that's a plane quartic. Let me draw a picture. Suppose I have P2 here, have a degree 4 curve. So it's a complex curve, but I'm only drawing the real section of the curve. Okay. Everything is over a complex number. Okay. I have a CP2, I have a complex curve sitting inside, degree 4. Okay. And because this is a canonical embedding, so I'm using the section of the canonical line bundle. That means if I take any hyperplane section in P2, that means a line section here, I'll just cut out a canonical divisor. Okay. For example, I take this general line, I cut out 4 points. That actually gives me corresponding to a differential up to scaling, where the zeros are distinct, just P1 plus P2 plus P3 plus P4. I could take a special line, say, like maybe something like a bitangent. Then I'll get like 2 times P plus 2 times Q. In other words, now the zero type or the special differential or the special underlying divisor correspond to different line sections to my plane quartic. I have to assume X is not hyperelliptic, otherwise this fails to be an embedding. It would give you a double cover of a plane conic. But I already discussed the hyperelliptic case, so here let me do the non-hyperelliptic case, but using this plane quartic model. Okay. So maybe from here, the line sections of, I'm still denote by X the image of the embedding. Line section of X correspond to canonical divisors, that is zeros of omega. Okay. In other words, each omega up to scale gives you a line section, and depending on the type, how it cuts X and the contact order at the intersection point, you get different type of canonical divisors. Okay. All right. So in this case, it is clear what this is going to be, right? I need a 1, 0 of order 4. That means I'll have a very special point where the curve has a tangent order 4. In other words, it does not meet any other point, only this point with contact order 4. X omega, this is X first is non-hyperelliptic. So I can switch to the canonical model. So and omega equals 4p, where p is called so-called hyperflex of X. That is, so there exists a line inside P2 such that L intersect the canonical embedding of X is really 4 times P. Okay. So this, I have to cook up a very special, say suppose I have a point here, I have a very high contact order. This is L, cuts out 4 times P here. So it is tangent to X at this point P, the tangent order is very high, it's 4 times P. If you only have 2 times P, that's ordinary tangent. If you have 3 times P, it's called a flex point. It's like a Y equals X cubed because it's flex point. 4 times P is like called a hyperflex, so like even higher than flex. Contact order 4. Okay. Right? So this is a description for the other locus. Let's count dimension. Once I know this dimension is also 6, then at least it would provide an extra component. Right? Because I already assume this X is not hyperelliptic. I discussed the hyperelliptic case. Certainly these two would not intersect each other. If I get equal dimension 6, then I'm done. Right? So now it boils down, say, using this model to check the dimension of this hyperflex point. Here's a standard way how you can check. Let's see. I hope I can do it right. So again, so the dimension of this out is equal to complex dimension. So how do you think of this? I mean, well, I can start from the space of plane cortex, okay? And if I say fix a line and fix a point, I require this degree 4 curve to intersect this line with exactly 4 times p. So that I can at least compute the dimension of such plane cortex. But then I have to modulo the extra automorphism of P2 that fix the point on the line. Okay, right? Something like this. Let's try to do it. So maybe I see. So again, so let's not forget adding 1 for rescaling omega, because this information is only about the underlying canonical divisors. So let's add 1 here, plus this is a rescaling omega. Okay, so this part, this line sections only give you the underlying canonical divisors, but my differentials can rescale, so this always gives the extra dimension. Plus, now what I want to do is I want to do something like 14. What is it? This is a dimension of the space of all plane cortex. I mean, I have a degree 4 plane curve. I consider the total space of degree 4 plane curves. But these are just degree 4 homogeneous polynomials in 3 variables. You can count the dimension modulo scaling. So this combinatorial number is 2 plus 4 choose 2 minus 1 is the total space of plane cortex. Okay. Now I want to impose a condition that so this X has contact order 4 at a given point P in a given line L. So what you can do is very simple. You can fix this line L by like one linear equation. Say, maybe suppose I have coordinate x, y, z. Or to use x, sorry. I have a coordinate z0, z1, z2. I can say L is given by z0 equals 0. And even in alpha coordinate, I could say x, L equals like one linear equation. Then I set P to be the origin. And when I restrict x to L, just means I set one coordinate to be 0, and I will get this polynomial is divisible by the other coordinate raised to the 4th power. So that means it will cut out exactly the origin 4 times. If you think about it this way, so for fix, so I fix a line, fix a point. Going through a given point, impose one condition. You just plug in the coordinate of the point into the equation of x. I require a tangent to a given line at that point will impose one more linear condition. And 4p just means I will in total have like 4 conditions. Right? So that's 4. That means this is like I get x dot L equals 4p for there's the conditions coming from this for fixed p L, okay, and fixed L. Well, I mean, see if maybe let me put it this way. So I don't want to fix my point P and L. Right? I can also take another line L and P, then get a different cortex, right? If I vary P and L, right, I can get some extra freedom for P and L. So I get P varies in one dimension in L, or vary in P, L. And if I want to choose a line in P2 that is a point in the dual P2, right, I get 2-dimensional for choose L in P2. Okay. In other words, I really consider like a correspondence of 3 objects, a varying point P in a varying line L, such that this cortex curve X intersecting L equal to 4 times P. I'm saying I have this dimension comes from the total space of X. This dimension comes from P varying in the line L. This dimension comes from varying L in P2. And this condition means I have to impose 4 linear independent conditions for any fixed P and L that will impose 4 conditions to X. But then I have automorphism of P2, right? I only consider abstract genus 3 curve, but my canonical embedding depends on the choice of basis. In other words, I can modulo this picture by automorphism P2. But automorphism P2 is PGL3, which is 8-dimensional space. I have subtract 8. Sorry, writing is a little messy, but this last part is the dimension of the automorphism group of P2. Okay, let's check all together. Hopefully I get the right number. So this is 10 plus 1 plus 2, 13 minus 8, 5 plus 1, 6. That means a quick check, you can actually compute this dimension in many other ways. If you know a little bit about the geometry of Gen3 curves, you know the locus of hyperflex points in the modular space is of certain codimension, you can just compute it. It means special versus points, you know. But anyway, so this also gives you an elementary computation. So this also equals the dimension of the total space, right? And also the curve x here are not hyperelliptic. That provides you another component. And this description also tells you this locus is connected, irreducible itself. Because certainly P in L in P2 is some kind of irreducible object, like a flat variety, then these are just some linear subspaces. You get irreducible space. Okay. I mean, with just a little more check, you can just justify there's no other component in this case. If x is hyperelliptic, then actually forces this point P must be a vertical point. If x is not hyperelliptic, using this canonical embedding, that forces you must have this hyperflex. So there are only these two cases, but there are like different components. Okay? Any questions?
So in M3 both are codimension 1, right?
In M3,
because hyperelliptic locus is also codimension 1.
Yes.
With this condition is also.
Yes.
And then one adding by this.
Yes, yes. That's right. Right. Hyperelliptic case in Gen3 is codimension 1. This means one, like a more special versus point is also codimension 1. Okay. Well, I haven't explained this index odd, right? Because so far this is just plane curve calculation. But there's another more intrinsic way to say it. So let me explain. Say it again?
Odd zeta characteristic?
It's corresponding to exactly odd theta characteristic or odd spin structure. So let me explain, because that can generalize in higher genus and other zero type. So maybe let me erase this. Again, for this case, so I have this component H for hype. In this case, you can check that in this case, actually, my point P is a special versus point. You can check that the dimension of the global section space of X. Now I consider 2 times P. So keep in mind, so I have 4 times P is a canonical divisor, right? Is a canonical divisor. So 2 times P, in a sense, is a half canonical divisor. And also called it's called the theta characteristic. So you can check that if X is hyperelliptic and P is a vertical point, this is exactly the double cover to P1, right? That means it has to have complex 2-dimensional section space, so that this pencil gives you like G12 maps to P1. This is 2-dimensional. So this number is even. So this rank of this half canonical divisor is an even dimensional space. And for the other one, it's for odd. The dimension, you can check that in this case is shunt X and 2P. Again, using the plane-quartic model, so you won't have like 2 different sections. Otherwise, that means at the point P, you'll have like different tangency. But you only get one very higher tangency given by this hyperflex tangent line, so this is only 1-dimensional. You won't have another special section. So this is odd. Okay. And there's one fact I won't proof here, but I will give you another more geometric interpretation using flat geometry. So in general, if you have a phase characteristic, that means the square root or the half canonical divisor, then this dimension of the section space is a deformation invariant. So this is another fact I won't be able to prove here. So say if so L is a line bundle. Maybe let me put it this way. L is a sorry. Let's see. LT is an irreducible family of line bundles on G-Riemann surfaces such that for each line bundle LT, its square is a canonical line bundle for all T. Then this global section space, the dimension may vary, but the parity mod 2 is invariant. So that's called XT. Mod 2 is invariant. It's a deformation invariant. In other words, if I have these families of even theta characteristics, because I know 4p is a canonical line bundle, I take 1/2. This 2p gives me a line bundle, which is half of the canonical line bundle. So these two, they have different parity mod 2, so they never intervene each other, assuming this fact. This was actually a classical fact dating back to Atiyah, and also independently by Mumford. And also later on, there's a topological version of it that I'll introduce soon due to Johnson. Okay. So this is also called spin structure. So I'll only mention the characteristic from the algebraic viewpoint, also called spin structure. Okay. From a topological viewpoint, you have to work with, I don't know, like the unique tangent bundle and do something there. Okay. But anyway, so assuming this fact, this theta characteristic, the dimension of the section space mod 2, so either 0 or 1, even or odd, is a deformation invariant by looking at these two global section dimensions that tells us these two things. They will certainly be disconnected. They cannot, like one cannot contain the other. But actually, let me provide an interesting, let me see, well, maybe let me first generalize the statement to higher genus and general signature mu. So what are the at most 3 connect components? As you can see, in general, I will have something like a hyperelliptic component. Then if the signatures are all, the entries here are all even, I can take 1/2 of them to cook up a half canonical divisor that is theta characteristic. Then look at the the spin structure, that is this guy, mod 2. Right? In other words, I have 3 structures being hyperelliptic and non-hyperelliptic, but like an even spin or non-hyperelliptic odd spin. So this is actually the special case because the genus is very low, then this hyperelliptic and this even spin, they coincide in this component. But for higher genus, you may have like 3 distinct components. So and this only happens when the entries of mu are all even. Otherwise, I cannot take 1/2 of it to be integers, right? So maybe I'll put in general this remark again. So this is essentially the content of the theorem of consistent Zorich. And the harder part is to show that besides these 3 structures, there's no other components. That actually is much harder to prove. So their proof is very transcendental. It's not algebraic. You have to do some surgery on this flat surface. Okay. Anyway, so let's put this remark here. So when mu has even entries, something like 2k1 and 2k Zn. So k1, if I take 1/2 of the canonical divisor p1 plus knpn is a half canonical divisor. So the parity, that is the dimension of the global section space, mod 2, distinguishes two, in general, possibly two kinetic components. Called like odd and even spin structure. Okay. So the spin structures, they show up only when all the entries are even. You can take the half canonical divisor so that the Caesar characteristic becomes deformation invariant. And also for some other special signature like this, you can also cook up like a hyperelliptic component. You have to make sure the locus of this hyperelliptic component has the same dimension of the total space. So if that matches, then you'll have additionally hyperelliptic strata. And also for, I'll just be vague for special mu. So if the hyperelliptic locus has the same dimension, equal to the dimension of total space, then so you get there exists also a hyperelliptic component. Okay, so in total, so we only see these three special structures, either it's odd or even spin or hyperelliptic components. That explains at least why we see like at most three components. But it's, three components in principle, but it's harder to show that there's no more structures. So that I won't be able to prove. But hopefully this example tells you at least these structures give you extra components, but you don't get, in some sense, you don't expect to get more than three. Okay. Any questions?
So for attribute is always pure dimension?
It's always pure dimension because the local coordinate works for all components. Yeah. That part is pure dimension of 2g plus and minus 1. Yeah. That's right.
The conservative result said that these are the only different components?
Yes. If it happens, it can only be caused by these structures. So that's that is really the true content of their theorem. But their method is transcendental. They have to do surgery. It's not algebraic. And they only work with complex numbers. If you change the field, then I'm not sure whether the proof still holds. Okay. So just in case some of you are more interested in topology or geometry, let me actually provide another interpretation of this spin structure, relating to flat geometry, because I know the form omega corresponds to a flat polygon, so you should be able to read off. And hyperelliptic is some sense easier, so you just need to read off this double curve to P1 from some symmetry of the polygon, right? But for the spin structure, how do I know which one is even, which one is odd? Okay, so let me actually give you interpretation. This essentially, I guess, following maybe Johnson's idea. Okay, I'll keep this. I'll just put it here. Now let's see. This is a flat geometric explanation, maybe definition. Of spin structures. Okay. So I define spin structures here using this more algebraic way, right? I look at this half canonical line bundle and look at the section space mod 2. But again, this comes from the underlying theory of a differential form. I look at the polygon. I claim I give you another way to read off the spin structure. I can read off whether this is even or odd. So what can I do? So I take X, which is in G Riemann surface, right? Again, I take a basis. Now I take a symplectic basis of the absolute homology. So let say alpha 1 up to alpha g and beta 1 up to beta g being a standard symplectic basis. Of H1x. No marking, just the absolute homology. So what is symplectic basis? Just means alpha I dot beta I equal to 1, otherwise 0. Only for the same index as well. Okay. So for example, you can easily come up with this basis. I mean, in Gens 2, I mean, you can take this to be right. Here's alpha 1, alpha I, beta I. Okay, let's just take a basis. So far, it's only topological information. I have not used any differential omega. Now let me take an omega with even zeros only. Right? I can only define spin structure when I have even zeros. Now suppose omega is a differential on X which has even zeros. So I still use the same notations to K1. Okay, on X. What I'm going to do is that let's just write down the polygon presentation of omega. And I want to look at representative, like a closed curve on X that represent each alpha I or beta I. And then because I have this flat metric, I can take, say, a smooth representation of this alpha I or beta I. I go around this closed curve. I look at the degree of the associated Gauss map. I mean, I look at the tangent vector along this closed curve. I map each unit tangent vector as a point in the unit circle and look at when I go around this curve, it goes around the unit circle how many times? If I goes around 0 times, I get Gauss map of degree 0, otherwise I get how many times, so this gets the degree of the Gauss map. Okay? So let me write it down. So for a smooth curve, closed curve, simple closed curve, X omega, I have this flat metric. So maybe let's give names gamma. So let the index of gamma be the degree of the Gauss map associated to gamma. Okay, for example, if I just have the standard unit circle sitting in the Euclidean plane as my gamma, I go around it once, I just get the degree 1. Okay. If I pull back, we are like a double cover branched at the origin, let's go around upstairs, I'll get 2, something like that. Okay. All right. Now let me define an invariant, some number for X and omega, okay, using the indices of the chosen symplectic basis. I mean, I won't be able to prove all the details for you, but at least I'll convince you. I mean, some part of it really makes sense, and using the information, I have even zeros only. Okay. Now we define this so-called the alpha invariant. I think Arf, if I remember correctly, was a Turkish mathematician who worked on some related thing. Let's just call it, like say A. This has something to do with X and also the differential form omega. To be, what I do is that I take this alpha and beta I and look at the index of them. X alpha I plus 1 times the index of beta I plus 1. And then I consider it mod 2. Okay. Then it's even, I get something like even structure, even spin structure. If it's odd, I get odd structure. I mean, essentially, you have to show that this definition coincides with the definition I wrote down for you using this algebraic, like line bundle dimension thing, right? So they all come from the same form, omega, right? The first definition I wrote down is using the half canonical divisor, look at the second space dimension. The second definition has nothing to do with, like it looks like nothing to do with the characteristic, it's just using the underlying Fleck geometry. So I won't be able to show the equivalence. Let me convince you why this only makes sense when I have even zero, because you have to check this definition is well defined, right? What if I change my curve, say, by passing some special cone point, right? Maybe this index may change and the invariant I define maybe not well defined. It depends on some choices, right? But let me at least say just only one thing. This is only a statement remark. So since omega has even zeros only, maybe let me put it this way. I have some closed curve gamma. When I deform gamma by passing like a zero of omega, by passing a cone point, it only changes the index of gamma by an even number. So when I consider mod 2, it does not change it. So gamma is still some simple closed curve there. Gamma varies and passes through. I'll draw a picture for you. An even zero. The index of gamma only changes by an even number. Okay. So let's check that. So suppose let's do a very simple example. I mean, even like naive example. I could consider an ordinary point as a zero of order 0, right? If I want, right? I mean, it's not vanishing, but it's 0 of order 0. Suppose I have a say ordinary point. Let's call. I think even 0. Let's call it P. Say suppose P is ordinary point. So let's take say maybe a pass gamma on this side. Oh, what do I want to say? Yeah, so let's take a gamma here. Okay. And it looks like in this picture, the index gamma is just 1, right? That goes around it, just a unit circle. Now if I vary gamma, and through this ordinary point P, so I vary it, I change gamma to say P. This is new gamma. But still, it's 1, right? And well, now if P has if P is a 0 of even order, you check that when you bypass such even order 0, the change of the degree of the cos map, just using this flat geometry, the total angle around P, you can check that it only changes by this even number. So maybe let's do another example. It's hard to draw this picture, but let's try to do another example. Say, maybe if I have a P, a 0 of order 2, right? So remember, it's a 0 of order 2, I need 3 disks to glue together, or 6 half disks. So the geometry at P looks like. Maybe let me put it this way. Instead of drawing this half disk, I'll say topologically I have 6 half disks. This is my center point P. But these are all of angle pi now. So I have a neighborhood, but each sector actually under the flat metric is a half disk. So this is really my original half disk, but I present it in the topological way. So the center will be a total angle 6 pi, which is a 0 of order 2. This is my point P. Okay. Now if I have say a loop gamma here, and if I deform it by passing this 0, you have to check that. Then if you go like this, you come in and you go out. And because now it just looks like you add, maybe I should say, yeah, let's just do this. You come in and you go out. And originally you only have 2 pi here, you have some 2 pi here, but then you add the actual 4 pi. So for the Gauss map, that means you add like 2 to the degree of the Gauss map. So, but you have if you have an odd 0, then this would not be well defined, because when you vary your choice, some representative alpha, beta, then by passing a 0, somehow you change the index by odd number. So mod 2, it may not be well defined.
So if this omega is locally like a DCM, then index of this gamma passing through this point, then...
No, it depends on the choice of gamma. In principle, I don't know the index of gamma. I only know if I have a gamma nearby 0,
nearby data, yeah.
If I go passing it,
yeah.
And it will change exactly by the 0 order.
So the zeros of order.
Yeah, so if it's an even order, that's fine. Yeah, it's changed by the 0 order. That you need to maybe encourage you to do a better picture than what I did here. I was only trying to illustrate the idea. But anyway, so it's not so important to this lecture series. I only want to point out, in the sense that this object, differential, somehow has many interesting incarnations in different fields. So not only in geometry, not only in this flat metric thing, but also in some kind of topology and like other areas. So this is a good example that tells you have different interpretations for the spin structure. Okay.
When you define this index, is it related to omega?
Yeah, I need the flat metric to talk about these tangent vectors, and yeah, I have this metric here. Okay. Otherwise, I will only have a topological circle or close. I don't know how to define the Gauss map. I need the metric. All right. Okay, let's see what I want to do. I still have about 5 minutes. Okay, so. So let me introduce one really central object in the study of differentials, but actually this is not from geometry at all. So this was really due to people who do dynamics and analysis technical theory. So let me be rather quick here, but tomorrow I'll continue to give you more details and examples. So there exists a very special GL to R 2x2 non-singular positive determinant real matrices action on the space H mu. Okay. This action is very simple. You just take a differential here and present it using this polygon model. Okay, I'm gonna just do this example. Suppose I have this omega. Okay, to represent this x and omega. Right. As one point in H mu. And if you give me a 2x2 real matrix, which is non-singular, right? I can view this A as a what is a 2×2 non-singular real matrix? I can view it as a linear transformation on R2, right? I mean, I have these vectors as my edges of this polygon. I apply this linear transformation to change these vectors. Maybe let's say the V1, V2, blah, blah. And then I do this linear transformation, A as a linear transformation. On R2. Okay? But the key point is if I have parallel edges, if V1 is parallel to this V1, then after this linear transformation, it preserves parallel vectors. I'll get another maybe U1, U1, but they are still the same vectors up to translation. Right? The shape and the size of the polygon may change, right? So I make it another polygon looks like, I don't know, like this. Maybe much longer and thinner. But still I have this, maybe let's call it U1, U2, U3, blah, blah, as the image of corresponding V's. But since it belongs to the same strata, if this one is in H mu, look, so at least in this example, it's pretty clear I still get the same number of edges, the same gluing pattern, and the total angle adds up to be the same as a special point. Right? This will still lives in the same space H mu. Okay. However, the underlying complex structure may change because I have a real matrix. So this action is not quite holomorphic. So this may correspond to really a different Riemann surface. Really have to mark it by x, possibly x prime and omega prime. Okay. I mean, even if it takes the genus 1 case, right? You just take parallelogram, you change it to another parallelogram. That almost always change the underlying complex structure. Right? Here is the same thing. I mean, a more intrinsic way to say that is this action is that you take the real part of the omega and the imaginary part of the omega, and you apply this 2×2 matrix, and you get something like a real part of some omega prime and the imaginary part of omega prime. Just again, because this matrix is only real, in order to make the resulting omega prime to be holomorphic, you may need to change the underlying complex structure. That means this x prime may actually be a totally different Riemann surface than x. But the genus is the same. And the type of omega 0 type is the same. So it's a very natural action which preserves this stratification, preserves the 0 type of omega. So the action has a special name. So often people call this action, call it Teichmüller dynamics. Because this study has many connections to Teichmüller theory and videos in polygon and right, some more analytic transcendental stuff. Okay. And once you have a group action, so one thing you want to study is orbits, right? So tomorrow I'll introduce the general result and some most recent breakthrough about this orbit structure under this GL2 action. But I guess today, let me stop here.